So, let's get started. Very first notes for differential equations. First section that we're taking notes on today is just going to cover definitions and terminology. Okay, first definition we should probably discuss is what is a differential equation. So that's what we're going to start with. And you've seen differential equations before. You saw them in calc last year. This is just going to add on. Differential equation is an equation containing derivatives or differentials of one or more dependent variables with respect to one or more independent variables. Ooh. So what we're going to have to be able to do is classify differential equations. So there are a bunch of different classifications, and the way that we solve differential equations are based on the type of equation that you have. So next thing that we are going to talk about is how to classify. First classification is you can classify by type. Within type, there are two main types. The first type is called an ordinary differential equation. This is often abbreviated ODE. An ordinary differential equation contains ordinary derivatives with respect to a single independent variable. Anybody know or can think of what the other option is besides an ordinary derivative? It's a pretty broad word. What's the other type of derivative that we found? Or the new type of derivative that you learned last semester? Partial. Yeah. So that's going to be our other type. But before we write that down, here are some examples of ordinary differential equations. We might have dy dx is equal to negative x over y squared. Another one would be y double prime minus 2y prime plus 4y equals 0. That y double prime is just the second derivative of y with respect to x. Those are derivatives, like it says above, though, with differential equations. Sometimes you might have differentials instead of derivatives. So you also could have something like y minus x dx, add 4x dy equals 0. That's another one. So that's the first type. Second type, like Aaron told us, is a partial differential equation. So you might have the partial of u with respect to y is equal to the opposite of the partial of v with respect to x. Or you might have the second partial of u with respect to x, add the second partial of t with respect to y equals 0. So that's the first way to classify, is by type. And again, the type of equation that you have will help you determine how you're going to solve that equation. Second way to classify besides type is by order. And when we say order, we are referring to the order of the highest derivative. So here's an example. So we have two derivatives going on here. This first derivative is a second order derivative. This middle one is to the 5th power, but it has an order of 1, which tells us that this equation is a second order ordinary differential equation. I didn't ask you for that, but there it is. Second order because the highest derivative is the second derivative. Okay. In general, a general nth order differential equation can be represented by this would be implicitly. You can have a function. It may have x, y, dy dx, second derivative of y with respect to x, so on and so forth, all the way up to the nth order derivative equals 0. So those are the first two ways to classify, type and order. There's one other way to classify. Questions before I tell you last way to classify? Okay. Okay, last way to classify is a differential equation can be linear or it can be nonlinear. What we're going to do is we're going to look at what makes a differential equation linear, and if the conditions aren't met, then it has to be nonlinear. If it's linear, you're going to have a coefficient in terms of x multiplied by your derivative, and then you'll have another coefficient in terms of x multiplied by the next derivative, all the way down to a1 of x dy dx plus a0 of x times y is equal to some function of x. There are two things that are important for us to notice here. All of the coefficients are functions of x. So that's the first condition for something to be linear. All of your coefficients have to be in terms of x. The other thing that you will notice, and this should relate back to like algebra 1 when you learned linear, Algebra 1, when you learned linear equations, a linear equation at most had x and y. Didn't have an x squared, it didn't have a square root, it had everything to the first power. Same thing here. If we look at all of our derivatives are to the first power. And also y. Those are the two conditions to be linear. So both of those have to be met in order to be linear. So if either one of them is not met, then our equation is nonlinear. For example, we wrote this on the previous page. What makes this one nonlinear? Fifth power. So that makes us nonlinear because our derivative is not to the first power. That is classifying. Those are the three different ways to classify. We're going to do one example and then we're going to move on. Questions before we do our example? Okay. First example, you are going to classify by order, type, and you're going to tell me if it's linear or not. Our first example is x to the fifth. I'm just going to write them down. I don't want to say them out because it might give it away. So if you could just look up here. Okay, I'm going to give you 2 minutes. I want you to classify both equations. You need to give the order, the type, and the linearity. For the first one, I got third order, ordinary, and linear. Good so far? Third order, order, and linear. Second one, I got nonlinear, second order, partial differential equation. All good? Great. It's the first part of today's notes. Questions on that before we keep going? Andrea?
You know how in the equation for the linear one, it says that it has to be equal to g of x. If say like for a, if it was like equal to e to the power like xy, would that be nonlinear?
Such a good question. Yes, that would be nonlinear.
If it were just equal to 0, would it be linear?
Linear still. Okay, good. Okay. Moving on. Oh man. Okay. Before we keep going, I want to tell you what we're going to discuss this semester. Pretty much everything is going to come down to one of two ideas or one of two goals. The first one I told you is we're going to be solving differential equations. So we are going to find solutions of differential equations. 2 notes for you. The first note is not every differential equation will have a solution. So just so you know, there are some that won't have a solution, and we will see those. Second thing for you to know is that we are going to be looking at ordinary differential equations. So you will have to classify partial ones, but we will not be solving partial differential equations. That's outside of the scope of this course. And then secondly, we will be finding differential equations that model physical situations. So like I said, the vast majority of the class is going to be solving. It's going to be goal number 1. But we will have some mostly physics-based applications where we are going to be modeling a situation. So next thing I want to talk about is what does it mean to be a solution of a differential equation? Okay, so any function f defined on some interval I which, when substituted, into a differential equation, reduces the equation to an identity, so just to a true statement, is called a solution of the equation. This is important on that interval, though, on that specific interval. So we are not going to be finding solutions yet. There's 2 things you're going to have to do. You are going to have to be able to verify that a function is a solution, and then there's a little bit of classifying of solutions. So, going first to verifying. We are going to verify that y equals 2x to the 1/2 minus x to the 1/2 natural log of x satisfies the following differential equation: 4x squared y double prime plus y is equal to 0 for all x greater than 0. Okay, all x greater than 0, that tells us our interval. So our function is defined on that interval because we have natural log of x, so that's what restricts the domain. So if we're looking at our differential equation, ultimately we're going to have to find the second derivative. So that's what we're going to start with, finding the second derivative, and then substituting in and seeing what happens. If we start with the first derivative, we're going to end up with 2 times 1/2 x to the negative 1/2 minus, and then we're going to have to do some product rule. We're going to have 1/2 x to the negative 1/2 natural log of x, and then we're going to have x to the 1/2 times 1 over x, and that gives us 1 over root x subtract natural log of x over 2 root x, subtract 1 over root x. So our first derivative then, if I write it a little bit differently, is going to be 1/2 x to the negative 1/2 natural log of x. We good so far? Okay. Second derivative, again, we're going to need some, this is a negative 1/2. We're going to again need some product rule, so we end up with 1/4 x to the negative 3 over 2 natural log of x minus 1/2 x to the negative 1/2 times 1 over x. And if you trust me, I will tell you that simplifies to be 1/4 x to the negative 3 over 2 natural log of x minus 1/2 x to the negative 3 over 2. Now, all of that was just the back work to verify that this actually works as a solution. This is then what we will substitute in for our second derivative in the equation. So now we need to go back to that equation of 4x squared y double prime plus y equals 0. So this is the verifying part. So we get 4x squared. Our y double prime is 1/4 x to the negative 3 over 2 natural log of x minus 1/2 x to the negative 3 over 2. Y is just the initial equation. So the initial equation, that's 2x to the 1/2 minus x to the 1/2 natural log of x. And we want to know, does all of that equal 0? Okay, so when we multiply out then, we get x to the 1/2 natural log of x, subtract 2x to the 1/2 plus 2x to the 1/2, subtract x to the 1/2 natural log of x, and we do in fact get 0 equals 0. That is verifying solutions. Questions before we keep going with more definitions? No? Good so far? Like I said, I told you, I'm sorry, this is boring. It's just a lot of definitions. Okay. Next idea. This is something I said before, but I want us to write it down. Not all differential equations have solutions. So for example, if we were to look at y prime squared plus y squared is equal to -1, that doesn't have a solution. Y prime squared is going to be positive, y squared is positive. If you add them together, you're never going to get -1. So that's one that visually you can tell. It's not always possible to visually tell, but that's one where you can tell. What happens, though, if I changed that -1 to a 0? Does that differential equation have a solution? Andrea? Right, we care about the function. So if they're both 0, that's true. What would the initial function be then? So Andrea is telling us if y is 0, if y prime is 0, what function defines those two? I think you're overthinking things a little bit. Y equals 0. Yeah, y equals 0. Only solution to this is y equals 0. That's one that you just found by looking at it. That is called a trivial solution. Trivial solution. Trivial solutions you can find by inspection. We don't care about trivial solutions. So sometimes that's possible. That's not really what we care about, though. Next thing about solutions, there's two different types of solutions. There are explicit and there are implicit solutions. And these are exactly what you've seen before for explicit and implicit. Explicit can be written as y equals f of x. So this is going to be a solution in terms of one variable. An implicit solution is going to have your variables on the same side. We have one last example to do, and then we have some remarks, and that'll be the rest of notes. Okay, looking at implicit solutions. We've already looked at explicit ones. Show that x squared plus y squared plus c equals 0 is an implicit solution for dy dx is equal to negative x over y. So what we have to do is we have to find dy dx and make sure that we get what the equation is. So we're going to have to do some implicit differentiation on this equation I gave you. You're going to take the derivative with respect to x on both sides of the equation. So we get 2x plus 2y dy dx is equal to 0. So then dy dx for this equation is negative x over y, which is the equation that we have. So yes, implicit solution. Okay. Questions on that before we write 7 bullet points? It's the last thing we have. 7 bullet points. No, we're good? Okay. So like I said, at this point, I have a few notes for us, a few remarks. First remark, the number of solutions for a differential equation is typically infinite. Last example we did in the equation, it was x squared plus y squared plus c. That's infinite solutions. C can be 1, 2, 3, negative, a fraction, etc. So anytime you have that plus c, that's an infinite set of solutions. Next thing for you to know is solving a first order differential equation. So first order is going to be some function of x, y, y prime is equal to 0. This is usually going to yield a family of curves that is some function of x, y, and c equal to 0 as a solution. So again, that's like the solution that we just saw, x squared plus y squared plus c. That's a family. So then the next logical thought is, well, what happens if it's not first order, if it's just any order, nth order? So if we are solving an nth order differential equation, so this is going to be one that's a function of x, y, y prime, all the way up to the nth derivative. Generally, we can expect a family of the following form. It's going to be x, y, c1, c2, all the way up to cn. So this is referred to as an n parameter family of curves. Okay, some more definitions. A solution that is free of arbitrary parameters is called a particular solution. So for example, y equals c e to the x. That's a family of solutions because it has the c. If we choose c to be 1, that gives us the solution y equals e to the x. That is called a particular solution because it has no arbitrary parameters. A few more ideas for us to know. Sometimes a differential equation has a solution that can't be obtained So going on, sometimes a differential equation has a solution that can't be obtained by the family of solutions. Okay, so here's an example. If we have the differential equation, y prime is equal to xy to the 1/2. I will tell you that this equation has the following family of solutions. Y equals 1/4 x squared plus c, that whole quantity squared. Okay, so that is the family of solutions. It's called a family because it has that parameter c. It also has, though, the singular solution of y equals 0. So this is called a singular solution because there is no way to get that solution from this family.
So a family of solutions would have like a constant that just could be anything.
Yeah. Family is always going to have a constant. So again, singular solution cannot be obtained from the family. There's no value that you're going to choose for c that's going to get us to y equals 0. Y equals 0 we would also call a trivial solution. It's one that you can just see is going to work. Okay, questions before our last two bullet points? Okay, last two. Vocab-wise, it's important that we understand that there is a difference between what we call a function and what we call a solution. And this is going to be a pretty small difference. We can say that y equals 1 over x is a function where our domain is all real numbers except 0. We can also say that y equals 1 over x is a solution to a differential equation, which is xy prime plus y equals 0. When it's a solution, though, we need to know where it is a solution. So we don't say it's a solution for all real numbers. We say that this is a solution on any interval not containing 0. So that's a small difference, but it is a difference. Domain versus specifying your interval. Last thing, something I just want us to recall real quick. If we have f of x is the integral from 1 to 2x of e to the t dt, and I wanted us to find the derivative of that, what would the derivative be? What did we come up with?
I got 2e to the 2x.
Yeah, 2e to the 2x. If you remember, you can put the 2x in place of the exponent, but then you have to remember chain rule. Yeah.